if you recall, we had a mean value theorem for derivatives, which said that there's a place where the slope of the secant line is equal to the slope of the tangent line. Now we're going to talk about what's called the mean value theorem for integrals. And basically what this says is, let's say you have a function f of x. And I'm going to draw the same function on all three graphs here. And let's do three different types of rectangles. So let's do one rectangle that hits it on the left side. So that would be A here. So obviously this rectangle is an underestimate of the exact area underneath the curve. So really what we're trying to find is what's the area underneath the entire curve here. Now let's do a right-hand rectangle. So if I do a right-hand rectangle, that would be an overestimate of the exact area underneath the curve. Now, what the mean value theorem says is there is actually a place, an x value of c, where you can hit the curve, and that area of that rectangle is going to give you the exact same area as the area underneath the curve. So, algebraically, we can also write it like this. So this is the exact area underneath the curve, which is the shaded yellow region, right? The definite integral, as long as it's above the x-axis, represents the area underneath the curve. And notice what this represents. F of c is just the height of that rectangle. So this is your height of the rectangle. And then b minus a is just the width of the rectangle. So algebraically, this represents what we've got going on here. It's saying there is a place where the area of the function underneath the curve is the same as the area of the rectangle. That's all this is saying. Now, we can algebraically manipulate this to find f of c by itself, just by dividing by the b minus a. So this will be another version that you will see. So this, again, is just saying that if you have a function that is continuous and differentiable, you can go ahead and find a rectangle that's going to give you that same area underneath the curve. Now, let's go ahead and think about what this f of c represents. So this f of c is really the y value on this function, right? That was the height of the rectangle. So really what it represents is the average y value on this function. You've got all these y values from here to here. So that f of c is actually called the average y value. And think back about how you find the average. We add up a bunch of stuff, divide by how many things you have, and that's really what's happening here. That definite integral, it's a Riemann sum. You're adding up a whole bunch of stuff, and really you are dividing by that interval. So that's how we get that average. So let's go ahead and do one algebraically. So I want to find the average value of this function on the interval from 1 to 3. So 1 to 3 is from here to here. So in order to find the average y value, this is your average value for integrals. We are going to go ahead and integrate the function from 1 to 3. And we're going to divide by the interval, which is 1 over 3 minus 1. Okay, so let's go ahead and do this algebraically. So this becomes 1/2. Antiderivative of 6 is 6x. Antiderivative of x squared is x cubed over 3. And I'm going to go ahead and evaluate this from 1 to 3. So I plug in the upper bound first. So that's 18 minus, this is 27 over 3, which is just 9, minus, plug in the 1. And if you do this algebraically, the arithmetic will give you 10/3. So this gives you 5/3. So what this is saying is we are finding the average value. It is the y value. So this is saying from 1 to 3, the average value is 5/3, which is like 1.66 repeating. So from here to here, the average y coordinate is 1/5.